Hi everyone, welcome to, I think, lecture 13 of CS287 Advanced Robotics. Today we have a guest lecture, Wolfram Burgard. Wolfram is professor at the University of Freiburg, is also leading a lot of the, well, I don't know how much detail I can say, but a lot of the AI and robotics efforts at Toyota Research Institute here in Mountain View. Wolfram is one of the pioneers in probabilistic robotics. Robotics used to be not so probabilistic until Wolfram, Sebastian, and Dieter Fox wrote the Probabilistic Robotics book, which is linked on our course website, which really introduced the whole community to probabilistic methods to doing robotics. And so it's a really great pleasure to have Wolfram here today, as he's the world-leading expert on many things, including particle filtering, which we'll cover today. And so we'll be able to learn directly from the world expert, which is really nice. Please join me in welcoming Wolfram.
Thank you. Great. So I hope that sound is on. I don't hear it exactly. Yeah, it's good. Oh, we are done. Thanks for coming. It's a great pleasure for me to be here and give this lecture about particle filters. A little bit of the context, and we are going to talk about the math behind it, the algorithms behind them, and then also like seeing a couple of examples of particle filter in practice. And if you want to know about application examples, then I can directly tell you about what I'm actually doing here in the Bay Area right now. I'm working for Toyota Research Institute as VP for automated driving technology, and in fact, like building real robots that operate in the real world, and like robots like those over here. For those who need actually basically the technology that we're going to talk about in this lecture. And if you want to work with a robot like this, talk to me afterwards. Okay, so what is behind this lecture? Usually when you build a robot that needs to operate in an environment and doing this in an autonomous fashion, then it is usually helpful if the robot knows about its own state and maybe also about the state of the environment. Today we're going to mostly talk about the state of the vehicle itself, and the other like more extended version of that is only briefly mentioned, but in principle the math behind this is exactly the same as we're going to talk in this lecture, and the algorithms that are used are also the very same. The only difference is the representations, and there's a particular trick that makes estimation in higher dimensional spaces more feasible. So we're going to briefly recap the recursive Bayes filter, hopefully known to all of you, and answer that or attack that question of how to actually represent the belief of that as basically a probabilistic way or probabilistic belief that we are representing equations in a few seconds. Typically, you also want to know how to maximize it. We are not going to address this in this course or in this lecture today. But we're going to talk about particle filters as an efficient way of representing such a probabilistic belief, and in particular in situations where this belief doesn't look like a bell-shaped curve and is rather a non-Gaussian distribution. The key principle of that is that we're going to have a discrete approximation of that belief by the so-called set of hypotheses or particles. Mathematically, it's actually not a set, it's a multi-set, because we cannot guarantee that two hypotheses are exactly the same. So please apologize for this slight inaccuracy of notation there. But it is actually easier to speak. And what we additionally are going to use is the so-called survival of the fittest scheme. Maybe if you have heard about genetic algorithms or evolutionary strategies, it's very, very similar, but what is going on in that representation in particle filters. Brief recap about Bayes filters. What we are interested in typically is we want to have a belief about the state of the dynamical system, and this is basically something like a posterior distribution about the state given all the actions that system has carried out and all the observations it has made. And so U's are the actions, and Z's are, or Z's are the observations. Could be camera features and camera images, distances recorded by LiDARs or ultrasound sensors. Whatever sensor you have, this could be the perceptions and the actions of a mobile robot, for example, are like the wheel turns, and that then using odometry or odometers are like turned into like angles per second, and from that you can actually calculate what action the robot might have carried out based on these wheel turns. All right, and using a couple of like mathematical derivations, Bayes' theorem, a couple of independence assumptions, law of total probability, and another 2 Markov assumptions, right, you end up basically with this equation down here. And the nice aspect of this equation is that it is actually recursive. So what we're interested in is the belief, or here we are, the belief at state at time t, and we can reduce this to this equation over here, where we do have the belief at time t minus 1. And there are 2 components in here. The first one is this integral, and the second one is like this multiplication on the left-hand side. And the terms are, this one over here is, we call this a transition model. It's basically the probability that you end up in state xt, given your executed action u at time t, and were in state xt minus 1 before. Right? It's a probabilistic way of representing the actions. Yeah? So if you carry out an action, then I want to actually describe the distribution about where I might end up given I was in xt before and executed that action. It's also known from Markov decision processes, reinforcement learning, all these kinds of approaches. And this term over here is a so-called observation likelihood, which is the likelihood of observing this measurement z at time t, given we are in state x at time t. And for those of you who like neural networks, there's one operation that is also like typically present in neural networks. This is this part, this integral over here. It's basically nothing else than a convolution of that previous belief over here with this probabilistic transition model or motion model. And, so we basically integrate over all potential prior states, multiply those with the probability that we end up being in xt, given that prior state, and then we multiply that resulting state with the likelihood of that observation. And this eta over here is a normalizer making sure that the belief sums up to 1 overall xt. And it falls out of this Bayes theorem. It actually can also be analytically calculated, and in implementations of this, it actually falls off while you actually do this calculation. So even in the particle filter implementation, we will later see this normalization happening in the algorithm. So this is basically how you can do like recursive Bayes filtering estimation for the estimation of the state of a dynamical system. That doesn't answer everything. So typically what we need to specify for actually making that work on a real system is that model over here, the transition model. We will briefly speak about how they can be represented. And also the observation likelihood function, right? What is the likelihood of making a specific observation given we are in a specific state? Both are really complicated typically, and the best way of obtaining them is to use statistics, making lots of experiments and figuring out how they actually look like, and so that we can in the end use them in this recursive Bayesian filtering scheme. In addition, what is unknown is what the prior is. So usually, if you do not know anything about the state of the system, you would assume that this is a uniform distribution. So robot can be everywhere, or the system can be in every state with an equal probability. And but the final question is how to actually represent this belief. What is the data structure that we are using in order to represent that belief? And there are a couple of implementations on the market, and one of the most popular ones actually is the so-called particle filter. That what we are not going to discuss in detail here is how to maximize this belief. So we will actually, if you are interested in the maximum likelihood answer, right, based on all the information that you got, that is something that we are not going to cover in that lecture. It actually requires another additional lecture. Even like things like this transition model or the likelihood model, you can dive very, very deep into those and have like separate lectures about how to actually properly represent these type of models or more advanced versions of those. So if you think about like an application of this in the context of robot localization, right, this is a very, very simplistic example of a robot living in a one-dimensional corridor, and all that the robot can do is actually moving forward and backward in that corridor. You could imagine this being like a cleaning robot, vacuum cleaning robot that does nothing else than collecting all the dirt in the corridor. And if you want to do this in a systematic fashion and not just moving around randomly, then you might use the position of the vehicle in order to figure out which places you covered and which not. And for that, the robot actually needs something like a probabilistic belief. And if you imagine that you switch the robot on in the morning, robot doesn't know anything about where you put it, then it might have something like a uniform belief about its current pose in that one-dimensional corridor. So the robot, in addition, has a sensor, and someone programmed a relatively simplistic likelihood model for us, which basically says when there's a door in the camera image, right, then the system says, yes, I'm in front of a door, and then when it's not, then the hope is at least that this system says I'm not in front of a door. But we are only using door detections here. And because we have also created some sort of a statistics, like how often this door detector actually fires. And this is basically nothing else but that function over here. Basically, the closer you are to a door, the more often it fires. So this is basically the likelihood of observing a door given that detector, depending on the state of the vehicle in the corridor. So now let's assume that we switch the robot on. Just by chance, it is in front of a door. Right? The camera fires and says, hey, I see a door. So it's basically that what we are observing is this measurement over here, this Z. So, and our likelihood model looks exactly like this. And we are now starting with the left-hand side of that equation. We're basically like inferring from that, given that we had a uniform prior, which is instead of this integral here, we have having nothing else but this uniform function. Right? And P of Z given X is a function that basically looks like this one over here. It's actually proportional to that. So what we do now is we multiply our prior with our observation likelihood model and normalize it using this constant that I named alpha in this term. And what we end up having is a distribution like this over here. So it's actually the belief then does not look any different than the observation likelihood model apart from a constant factor. So now let's assume that the robot moves forward. The robot starts actually moving, and typically actions increase uncertainty in most cases. There are exceptions. So if I keep going, if I don't know where I am, and I keep going for an hour forward right now, then it's very, very likely that I'm stuck in front of a wall in this room. Right? But usually, it increases uncertainty. So if there's only free space and I keep moving, then because of the uncertainty in my movements, I will increase the uncertainty about my pose. And you can regard this as a convolution operation. It's basically this integral that you see on the right-hand side. What we're doing is we're taking our current belief and convolving it with this transition model. We are basically calculating for every position, taking the belief that we have been at another position before, and multiplying this with the transition model that we end up in X, given we were in X prime before. There's nothing else but convolving this, or you can imagine this as a process of convolving this distribution over here and shifting it according to the movement. That would be a very, very naive implementation of this, but in principle, you basically need to calculate this integral over here. And which means that this convolution operation kind of typically smoothes things out, and you get a distribution that is shifted and a little bit more flat. So the peaks are not that high anymore, meaning uncertainty has increased. Now let's assume when the robot passes the other door, the next door, the camera fires again. And that what we need to do now, we calculated this integral over there, just basically this function. We get another observation. We basically need to perform this multiplication on the left-hand side. And what we are basically doing now is we are multiplying those two functions over here to obtain this one down here. So this is basically that operation of the base filter. And once we normalize this, then we end up having this function over here. And what you can see from it is basically we end up having 5 peaks in that distribution. Like one is consistent with 2 observations. There's this one over here. And the other 4 are only consistent with just 1 observation. And the interesting aspect is some are a little bit smoother than the others because they were the first observations and after movement, so they have been convolved, whereas those have not been convolved thus far. Well, this is kind of like how this function, how we obtain this function. This directly comes out of this equation up there. And the hope is that as time goes by, right, and we collect all the measurements and move around, the robot will get more and more certain, meaning that this distribution peaks and in one state so that we can actually have a high certainty about what the current state of the vehicle is. But that doesn't necessarily need to be. It can even be that in ambiguous worlds that the robot actually doesn't know in which state it is because 2 rooms are absolutely identical and keeps moving in one of these 2 rooms. And then the robot actually cannot tell in which of the 2 rooms it would be. And that means that this distribution has actually 2 peaks. And then there's nothing the robot can actually do other than reasoning about its uncertainty and trying to figure out which actions it needs to carry out in order to minimize that uncertainty, which is kind of like that what people do in active vision, for example. So key question is, and that's what we're going to answer in this course, is how can we represent such a distribution? And which means that we need to do some function approximation. And an interesting way of representing distributions is using particles or so-called samples. So imagine that we have a distribution like this function f over here, and we want to represent these by samples, this distribution or function, then that what we can do is basically have higher density of hypotheses or particles in places where the function has a high value and a lower density where it has a low value. So basically what that means is that if we integrate locally or we count the number of hypotheses locally, then that gives us an approximation about what the actual function value is. So and you can do this with arbitrarily shaped functions. Techniques like these are used, for example, when you do integration. Monte Carlo integration is, if you know this, is very, very similar to that. Basically sample randomly and then you evaluate the function, and that gives you in the end the area under the curve. But this is something here we just collect these or have samples that are actually more dense in places where the function has a high value and less dense everywhere else. And the key question is, how can we get such a distribution? So how can we get hypotheses or samples that are distributed according to a specific function? Different ways for doing this. One very, very popular approach is the so-called rejection sampling approach. So let's assume we have this function f over here, and we want to have samples that are distributed according to that function. And usually you apply schemes like this for functions that are easy to evaluate but hard to sample from, right? Which, for example, is the case for a motion model. Right? That can be an enormously complex model that you can, it's an analytical function you can easily evaluate, but it's hard to actually generate a distribution of particles from that function. And rejection sampling works as follows, right? You basically sample in that interval of interest, like a uniform value. Let's assume that is x in this case. You again sample another value, that's a so-called y value, that is lies between the max of that function and 0, right? Which would be this is f of x, this would be this constant c over here. And then you make a very, very simplistic test. Namely, if f is larger than c, then we keep the sample, otherwise we reject it. Which means that if this comparison over there makes sure that in places where this function is very, very low, there's a very high likelihood that this sample is rejected. And So in cases where the function is high, there's a higher probability that it is kept. So we drag that x, we draw another x, like we have f of x over there, x prime, and we sample c, and then f of x prime is larger than c over there, so we keep that x. So this is basically rejection sampling. Any idea which type of function is the worst case for this scheme? The professor was first, but I asked the student. A uniform distribution. Let's assume we have a uniform distribution. So it's a constant value. Right? We do have like any type of constant that is beyond that. Right? Let's say that the max of that uniform distribution is A. The max that we sample from is B. Right? The ratio that we keep that sample then is, I think, A divided by B. Right? Something like that. That is, depending on where B is not that bad, right? If B is close to A, if B equals A, then it's actually, the probability is 1 that we keep it, right? So that is actually relatively, basically the best case that can happen, right? But what is the opposite of that? Uniform. What?
Delta.
Yeah, it's a Dirac distribution, right? Or it can be like a sum of Dirac distributions, like if you have only one peak where all the probability mass accumulates, right? You basically, so that you have just one peak over here, we have this going to be sample one over here, it's 0, you withdraw it, right? The chance that we hit exactly that peak in a continuous world is virtually 0, right? How long will this algorithm run? Forever, good. Huh? So you actually need to keep track of that, right, when you implement it. So don't be naive, right? If you use it, it can actually, depending on what your function looks like, can be enormously complex. But the advantage of that is you can sample from an arbitrary distribution, which is pretty cool. The other thing is, like here in this, and this is why this is important, in a computer, every programming language typically has a way to sample from a uniform distribution. It's your RAND operation, or however that is called in your favorite programming language. Samples from a uniform distribution. But sampling from any other distribution, right, we don't have a random number generator for, or a sampler for. Right? So this is basically a way, if you want to sample from, for example, a Gaussian distribution, you can exactly use this scheme. There are more efficient ones, pretty cool ones as well. But if you want to do this, then you can actually sample from an arbitrary distribution. But it's important here to see that we sample from a uniform one in that case. But there is a way to actually use non-uniform distributions as well. And this is the importance sampling principle. So like, if we want to sample from this distribution, we do not need to sample from a uniform. Let's assume we do have a way of sample from a more informed distribution, right? Like, the most informed distribution would be the target itself, yeah? F itself, right? So, what we are using is the proposal, this is the red one here, to actually, and the hope is that with the proposal we get as close as possible to the target, because then we get the samples already in places where we want to keep them. But the idea here is that we have a different distribution that looks more closely than F than the uniform distribution. The only thing that we need to do now, in addition to that, is take into account that we didn't sample from a uniform one. And in order to do this, we calculate a so-called importance weight. So we give these samples a height, or they look like towers, all of a sudden. And this is basically nothing else but the ratio of F divided by G. That's basically the height of these samples. So, and this principle is basically mathematically underlying the particle filter algorithm. So what we need in particle filters, the representation is nothing else but a multi-set, mathematically correct, of hypotheses, and importance weights, and one weight for every particle or hypothesis. Mathematically, like, because these are just peaks, right? We have this this weighted sum of these Dirac distributions over here. So this is basically the posterior that we're having. Just to give you one primitive example how that works is actually an example generated by Dieter Fox. It's the old times of robo-soccer with IBO robots. And at that time, they had the soccer fields with landmarks, and they had relatively simplistic landmark detectors, which was just using the color code. And you can actually estimate the distance to that based on the size of that color-coded field or segment in your image. And so then you get some information about the distance, but what you don't get, because these are circular landmarks, you do not actually, you only get the bearing to the landmark. You get actually bearing and distance, which means that you usually, when you observe a landmark, you get something like a circular distribution around that landmark, and the distance, the radius of that distribution is given by the estimated distance. So geometrically, for an observation, like when we see those three landmarks, 1, 2, and 3, and like get the appropriate distances calculated by the size of the segment, then like geometrically they would look like this over here. And what we're interested in now is like getting a probabilistic belief about where the vehicle might be, right, or the robot might be. Right. And if we do this like in a probabilistic fashion, like let's assume this is our P of z given x. There's actually that function expressed here in a discrete fashion, and you can actually see that by these pixels that in the image. Right? So again, like for a distribution for the landmark 2 and for landmark 3, and normally, like if we were able to just like get these directly, right, then we can multiply the 3, and then we get this distribution over here as a posterior about where the vehicle might be, based on just no movement, just the multiplication of these distributions. Now in a sampling-based world, right, where we have particles, right, we cannot directly do this anymore, because we do have these particles, or we want to reason about these particles. And what we need to do now is like stay in this representation and keep these particles as the belief over the state of the vehicle. And here is where what we want to have. We want to have samples that are distributed according to those 3 distributions. In fact, we could now like take those 3 distributions and multiply them and then sample from that result, but then that's actually not that what we would like to do, simply because the maintaining such distributions can actually be enormously complex, because they need, like, this is a 2-dimensional field that we need here, but in higher dimensional cases this can actually be hardly tractable. And so we are actually interested in just using particles and just evaluating those likelihood functions. And this is what we are that we want to have. So the idea is now to basically generate a set of particles from one observation, and then this is our proposal distribution, and then using the others, like the multiplication of the other 2 as the target distribution, of all the 3 as the target distribution, and then get the other 2, and then basically divide those, the resulting, like the importance weight of the first ones, which is uniform, by the or have the importance weights set to the likelihood of those 2 observations. That's basically what we are doing. So mathematically, we'll see this in a second. So we can sample from each of those, and let's assume we sample from 1, and what we were now interested in calculating importance weights, like let's assume we sample from the left-hand side one first, and then we calculate importance weights for those hypotheses over there based on those 2 distributions. But because of symmetry, we can use any of the 3 and then like calculate the importance weights based on the other 2. Mathematically, we are interested in a target distribution about like where the vehicle might be given all 3 observations. We do have a sampling distribution. We create samples from one observation. For example, this rejection sampling principle. And then in order to calculate the true distribution, we need to calculate the importance weights, which turn out to be the product of the likelihoods of all the other all the other observations, apart from the one we sampled from, which is basically in our case the other 2 arcs, right, or arc-like distributions. So, and if you do this, right, that would be the weighted samples for all three. In principle, what we do is we sample from we take one of the three and then calculate the importance weights of the other, and the resulting distribution might then look like this over here. So the key principle is we have kind of like a set of hypotheses, and we calculate importance weights for those. And you can now think about the result over here as something like a resulting set of hypotheses generated according to the importance weights. It's kind of like you could think about the result as being a deck of cards where you actually multiply every card according to its importance weight. So the frequency of a card depends on the importance weight that you have. Right? And then when you draw then from that deck of cards with replacement, you put it back in, right? You in the end get a distribution that is proportional to these importance weights. And this is going to be the algorithm that we are basically going to use. In principle, this is how it works. Right? And then you get this type of representation in the end. You could also regard of this that you increase the transparency of a particle with or decreasing importance weight. So the lower the importance weight is, the more transparent it is. And the result would look very, very similar to that one over here. I mean, you don't see semi-transparent particles here, but in principle, it's the very same. So how does particle filter localization work? So basically, we represent our belief by a set of hypotheses. Right? We take one of these hypotheses out of the hypothesis set, one of the particles. We draw it from that set. And then comes this step where we actually calculate a potentially new place for that particle. We say we propagate it through the motion model. Like x prime is the one that we get from this current belief, one of the particles in the particle set. Right? We sample a new potential place for that particle or state for that particle. In robot localization, that would be a hypothesis where the robot might be given the motion that it executed. So this is something that we draw that according to that distribution. Next one is we calculate the importance weight based on the observation likelihood. We look into our camera or whatever sensor we have and calculate what is the likelihood of that observation given that state that we just calculated. This gives our importance weight. And the next step is that we perform, and this is why we call this the survival of the fittest operation. We resample from that set, and we will later discuss how that works exactly. This deck of card principle, a deck of cards, and from that, and we get a new belief up there. And we basically repeat this process as long as we actually get updates from odometry or movements or sensor or perceptions. Right? So this is how it works. And in practice, and that's what we are going to do now in the next figure, this operation, because it's actually here we draw from the current belief, which in principle is a weighted set of particles. And there's a resampling operation, transforms this weighted set of particles into another weighted set of particles where the particles represent the very same distribution as the ones that we have already, however, with uniform importance weights. So usually what happens is we get towers of different heights, and this resampling operation calculates new towers that all have the same height but represent the very same distribution. So that is what is happening. Because we have to draw here and there, we basically perform this in one step. It's basically in the visualization that you see in a second, it happens as one operation. Coming back, to that figure that we saw. Sorry, I forgot to remove that animation here. But in principle, this is exactly where we need this particular operation. And once we have this distribution, let's assume we hired an undergrad for coming up with this distribution over here, and we use this scheme to actually sample from this. It's basically, he gives us that function, the implementation of that function, and we use this algorithm over here to calculate potentially new places for every hypothesis. This is the scheme that we're using for that. And then you basically we need another undergrad to implement that observation likelihood model. And once we have that, we can calculate the importance weights. And that's all you need to do. You plug this into your computer or into your particle filter algorithm. And then from there on, you can actually estimate the position of the vehicle in the real world. Let it be a car or your robot at home, whatsoever. Right? Here's another visualization. We saw this with the distribution. And here is the very same visualization with particles. Right? Initially, these are just randomly distributed particles. Doesn't matter if you use them, like if you calculate the uniform distribution by just going towards sampling them equidistantly, or if you just use your random number generator in your computer for doing that. This is the second version. So the next step is let's assume again we have the observation first. We calculate the importance weight as just the observation likelihood given that observation and the state of that particle or hypothesis. Right? So that's basically this is our observation likelihood once again. And then in the end, we get these towers with a height proportional to the observation likelihood. This is just because we normalize the weights so that they sum up to one overall hypothesis. Right? And now the next step is that the robot moves. And in that step, we actually need to pass the hypothesis through that motion model. So we sample new potential states from that. And at the very same time, we perform the resampling operation, this magic thing that converts weighted particles into a set of particles with equal weights that represent the very same distribution, ideally, right? Or an approximation, another approximation of that distribution with uniformly weighted particles. You will see how that algorithm works in a few seconds. Right? So what happens now is the robot moves forward, and we propagate the particles through that motion model, and at the same time resample in a way like with this deck of cards operation and get particles hypothesis distributed like this over here. Right? And again, if we have another observation, we weigh these particles, another movement, and then you see that these particles typically cluster in places that are consistent with movements and observations. And as our observations were consistent with the real world, we do have a distribution that is close to that what the true state is. So the particle filter algorithm is basically nothing else but then a procedure that uses particles for representing the belief or hypothesis, weighted particles. The weight is the target distribution divided by a proposal distribution that is, in the context of localization, is nothing else but, for one observation, the observation likelihood of the latest measurement given the state of the particle. And the resampling operation, this magic thing that we only implicitly talked about thus far, is the operation that replaces a particle set containing unlikely state hypotheses with likely ones, basically by drawing more likely cards from that deck of cards. And this is the algorithm over here. So we basically, the very first step is that we perform this resampling operation. This basically, we sample from the current set of weighted particles, a number which is basically the index of a particle, and we draw that particle with a probability that is proportional to that importance weight, meaning higher particles with higher weights are drawn more often than others. Right? This is this index J that we calculate. We then take xj, right, which is xt. We calculate xt from the previous one that we draw from that particle set, passing it through that motion model with the rejection sampling principle. We calculate the importance weight, which is proportional to the observation likelihood. We normalize the importance weights. Right? That's why we calculate this. We sum all the importance weights up and add this new particle to the new particle set. Right? And this is the normalization operation down here. And this is basically that what we are doing. Just to sum this up here, how this works is in the first place, what we are doing is we draw a particle from that existing set of particles. Right? We pass it through that motion model. We say we draw a new pose according to the pose of that particle and the action carried out by the robot. We get a new state or pose of the vehicle. Then we calculate the importance vector or factor, which is like if you do the math exactly, then it turns out to be just the observation likelihood of your measurement ZT given that state of the particle, and that gives you the that gives you the new set of the new belief. And let me see. The next is the resampling operation, and I was told that we're going to do a short break in between. 5 minutes, 7. I do always 7 minutes in Freiburg, which is like getting to the bathroom and back, and all the operations in between. 7 minutes. Okay.
That's good.
Let's do 12 at that, according to that clock. 57 according to mine.
What is this pointer?
It's pretty cool, man.
What does it do?
It has an IMU built in. You know what the advantage is? You do not need to point at the thing because you can see it on the screen as well.
It knows.
Yeah, and there's, you know, often you have these presentations where you have a big screen in front of you, then you can stand there and point there, and otherwise you always have to turn around.
Wait, you can point here?
Yeah. Wow. If anyone wants to try it, it's pretty cool. And you can program it. It also has a real, like a red dot if you want to, if this like dimming operation is to.
So it looks at something bright to calibrate on? Is that
No,
what
it is
does?
just like an IMU.
But how? Oh, but how does it?
How does it know where the screen is?
It is just like I think it initializes it at the last position, and then it takes your movements to
Oh, I
integrate.
see. When you click stuff, I click this way.
Yeah.
Oh, now it's in both places.
Yeah, it is in both because it is directly done on the graphics
I
card.
see. It just wherever you start is the middle of the screen or some part of the screen.
Yeah. So the only problem is when you have this presentation mode. Presentation mode means I now cannot see my next slide. So which is like the disadvantage. But I think it is also possible doing that. But it's my third presentation I'm giving with that. But it's pretty cool.
Yeah.
So particularly when you record things and you do a direct screen grabbing, right, then it's actually also in that. Otherwise, when people point at
Oh, so because it is recorded. It is recorded through here directly.
yeah,
So whenever
yeah, and do
you're
it
doing
there.
this, people watching it on the video see it too. Oh wow.
Peter, go buy one.
Yeah.
Yeah, I
I
bought
need to
one
get
for
one.
my lab as well, and it's disappeared. Yeah. You need to buy 40, I guess.
What is it called? Logic?
Logitech. It's a Logitech.
Logitech? All right. Oh,
super
next
fun.
lecture.
Yeah. But it doesn't work well with Hangout when you do these Google slides.
Oh.
You got a minute?
Yeah.
I'm a big fan of your works. My name is Yash. I work for Dr. Suka in the mechanics system control. For the past year, I worked on that basically. Yeah. A lot of hardware stuff. And recently, I'm thinking about a project for this class and also 285, which is mostly learning at Berkeley as well. And one thing I found you and your students 10 years ago, this is a long time ago, is use reinforcement learning to see which feature to keep or not. Yeah, it was really cool. But that paper was based on UKM.
Yeah.
So I'm more thinking about can we use the same methodology but applies it to like knowing up to optimization. So basically we have a better pool of features.
Yeah.
Yeah.
It should definitely be possible. And,
Okay.
I mean, the key from there is then how do you calculate this? Yes, that's true. But I guess it need to run the optimization instead. And then have some of the some features that you need to have like different state or results of that optimization in order to figure out which features are the right ones.
Right, because in that paper, I don't think it explains like how the experiment was carried out like in detail. I'm more thinking because we have a car ourselves and we have some challenges in San Francisco. So what about segment this into say like 20 seconds each? So I run a small application for 20 seconds and I compare with my run from whatever RTK I have, and then see like my final reward will go how close and then selectively removing the different dynamic features. All right. So because for the 285, the proposal was sent out, but I haven't had feedback. But for this course, I think the proposal can go out for like in 1 week. Oh. So I will send it to you and see how.
Yeah, maybe you can send it to me as well if you want.
Thank you so much for that. And I see you work for Toyota. I'm trying to apply for a job as well. Yeah, go for it. Yeah. Thank you so much.
Send me an email.
Yeah. Appreciate that, sir. Yeah, thank you. Fine.
Did you post that? Did you tweet that?
I tweeted my video started the lecture, but I want to record a video of you using your pointer.
Yeah.
I'll tweet that. That's
Good.
what I want.
Good. Let me do this on the next slide.
Is there a slide coming up?
Yeah, after that.
Okay.
You're tempted to actually point towards it, and that's why I was a little bit hesitant. And I'm not really used to it because this big button always goes forward. You need to practice.
I'll capture it. 5 second clip.
Yeah,
I think pointing there makes more sense though.
yeah.
And it looks like you have a flash here.
Yeah, that's true. 57. Way to go. We're German and start on time. Not really.
Which button?
Good. No, the Swiss would really start on time. Okay. So that operation that we haven't talked about in detail is this resampling operation, and this algorithm is also actually pretty cool. And how this is done. We're going to talk about two variants of that, and the first one is a rather naive one, and the second one is a little bit more fancy. And then we will talk about the difference or the properties of those. So what we typically have is we do have a set of weighted particles with uneven importance weights, and what we want to have is typically a set of particles that is distributed according to this weighted particle set with importance weights that are uniform. And the reason why we want to have this, assume that we let this algorithm run without this operation. Right? So these particles will basically spread out according to our motion model. We sample from that motion model, so the positions are determined from that sampling operation, or the states. And they all have different importance weights. And what happens is typically that some particles get into spaces of this, or areas of that configuration space of the system that is extremely unlikely. So we will have like very, very high differences or large differences between the importance weights. And some particles, basically, if you think about this distribution, are in areas where we have a very, 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 very low likelihood, which means that they actually do not contribute to to the approximation of that distribution. Removing these hypotheses would actually not help us a lot when it comes to like the accuracy of that representation. So what we want to have is basically particles that are close to the peaks of that distribution, so that we actually can get more details about how the distribution actually looks like. And this is why we need this resampling operation. And what we do is basically we take, like with these deck of cards, right? If you multiply every particle according to or proportional to that importance weight, and that depends solely on the memory that you have and the resolution that you want to have. And then we draw from this deck of cards randomly in order to figure out which particles should actually be in the new particle set. So this is basically what this operation is about. And from a more algorithmic point of view, that is we are in the following regime, right? We have like a set of particles, right? So W1 to Wn, and we arrange them now in a circle, and you can regard this as a roulette wheel, where the holes in that wheel are their size is proportional to the importance weight. And if you now throw a sphere into that roulette wheel, right, it will end up in these bins with a probability that is proportional to these importance weights, under the assumption, or exactly the importance weights when they sum up to 1. Which basically means, mathematically what we do is we just draw an angle, right, like this one over here, and then we need to calculate the bin in which that angle falls, right? So in this case it would be the bin 3, right, for particle 3 would be taken. Basically just you draw a card from that deck, and then it's basically the number of cards, equal cards in that deck is the size of that bin, you know. And so we repeat this n times, and by doing so, we get like n new particles. So the operations that we need to do is like drawing an angle, or if you arrange them in an array, all these particles, you actually want to draw a number between 0 and 1, and you want to know which particle is that, into which bin this number falls. Question is, how expensive is that operation? If you do want to implement that, right? Drawing an angle, figuring out which bin is it. What is the cost of that operation?
Order of the number of squares, particles.
For just that, the search is the number of particles. If you implement it in an array, you run through that array and check, does it fall into that bin, right? Yeah. That was what that's great. And you need to do this n times, so it would be n squared. Someone said n squared. Can you do this more efficiently? So I give you a hint. So imagine we, instead of calculating, looking just at the importance weight, we look at the right borders of the importance weights and their positions, right? Which basically is an ordered set of numbers, right? All we need to store in this array is just like where it ends. We get the start from the where it ends of the previous one, right? And if we do search in such an ordered set, that's log n. And the procedure is?
Binary search.
Binary search, yeah. So you can do this in log n, which is cool. Log is virtually constant for every number that we can imagine. But on the other hand, like if you sit in front of your computer, like students hate log n because even if it's a 10, it is like a factor of 10 that it takes longer. So that's why people don't like log. So that's basically that procedure. It's a roulette wheel, binary search, and log n is the operation. But there, interestingly, is a faster version of that. And this version works like as follows. So all we need to do is we need to sample one angle between 1 and 1 divided by n being the number of particles. And then we advance in a constant fashion, basically by 1 divided by n. And we do this n times. And wherever we, like every particle, like in whose bin we then step by doing that operation, is the one that we keep. And my argument is that this operation can be done faster than log n per particle. Why is that the case?
Could you say that again?
Yeah. So we start with 1 divided by n is the first angle, right? It's randomly chosen angle between 0 and 1 divided by n. That's this angle over here, like the difference from the vertical. And then we advance by 1 divided by n and check into which particle that falls, right? Or which particle's bin that falls. And then we advance by 1 divided by n again.
So this time it's just linear total because you search each of the spokes of the,
Yeah.
the wheel
And how often do we need to touch?
just once.
Yeah, some are touched twice, right? But some are skipped. But we never go backwards because we only go forward. Like we need this to do this n times. We actually end up like with an operation that is constant per particle. And this has another advantage, and we will talk about this in a very few seconds. So basically, these are different versions of this, and then this called stochastic universal sampling or systematic sampling has linear time complexity in the number of particles. And yeah, professors always tend to say it's easy to implement. Yeah, and has a low variance. And the low variance is actually the key. And we will talk about this easy implementation in a second. And I will point you to pitfalls there as well. I stepped into them as well when I implemented that. But it has low variance. So let's assume we have a weighted set of particles. And it doesn't matter now as to whether the weights are uniform or non-uniform. We just perform resampling operations. So let's assume what we do now is we have a set of particles, we perform a resampling operation, and then we repeat the resampling operation. Although these particles have the uniform weights already, nobody hinders us from doing this. Right? That would just mean that these bins have all the very same size. And now let's assume we go back to that roulette wheel. So what we are doing there is we are basically drawing angles and checking in which bin that falls and keeping that particles. And we are withdrawing all particles that don't get selected by this arc or this angle that we have there, by this arrow. So if we do have n different, let's assume it's different particles, and we perform this operation once, what is going to happen? In terms of, I'll give you no, this is difficult to answer. In terms of like the diversity of particles, let's assume we have n different particles and they are actually different. And we perform this operation once, drawing n angles. Like how many different particles are we going to have afterwards?
Slightly less than
No, like way less than actually.
How much that is, but it's not guaranteed that we will have n different particles, right? Right? And as time goes to infinity, right, how many different particles will we have if we do this infinitely often? Different ones.
Like only one.
Only one. Right? Which means that we are going to lose diversity. And in the end, we will have like just our function approximation will be just the Dirac distribution at the peak of that particle set. Ideally, doesn't need to be. Because just if we choose the wrong one, then we might lose the maximum likelihood particle. If you perform the very same operation with this scheme over here, so we draw an angle between, and now let's assume that all the particles have the very same weight, and we are n different ones. Right? The very same weight means the weight of every particle is 1 divided by n. Right? The first angle is drawn between 0 and 1 divided by n. And that's easy to implement, means we need to carefully think about the left and right border of that. Right? That would be in the algorithm in a second. So let's assume we do this correctly, like dealing with the borders, because if you exactly hit the border, if we choose 1 divided by n, we need to know is this the left one or the right one. We need to be consistent about that. But let's assume we have done this properly, like what is going to happen if we perform one resampling operation. All the particles have 1 divided by n as importance weight, and they are all different. We do this once, we have how many different particles? N. So this is why that says low variance here. You're basically like in keeping the variance of that particle set, and it is independent of how often we sample. It might be with this roulette wheel approach. In the worst case, we are going to end up, even after one resampling operation, we end up having a diversity of just 1 particle, because all the errors fall into just 1 bin. Nobody tells our random number generator that it is not supposed to do that. It has relatively low likelihood, but if you repeat that, right, then the variance about the particles that you're going to have is, with this approach, is substantially lower than with the left-hand side one. And it's faster. And coming back to easy to implement, this is actually how it works. Right? And you need to initialize these thresholds. And in this case, I exclude the 0 and include the 1 divided by n. And if you keep this being consistent overall, then you actually, and this is the operation where you actually sum up the C's, right? Over this is basically calculating the right-hand side borders of this. And then we run through the samples and skip the ones that we step over. That is this while loop over here. And the ones we end in are those ones we keep. And then we increment the threshold by 1 divided by n. We could basically go to the next error. And you can see here that we never go back. We skip over some. So in the end, we touch every of these CIs, which are calculated over here. There's the right-hand side borders of that interval. So we run just once over the entire particle set. Easy to implement. It's exactly that. Requires an afternoon, also depending on how skilled you are, right? And debugging and all these kind of things. But this is basically the operation that is typically used in that context.
Wolfram,
Yeah.
is there in any way that the other way of sampling would ever be preferred, or is this just strictly better?
I think I've never seen a case where the other one would be of advantage. You know, it is particularly when you think about, I mean, you're basically losing states and you're basically losing diversity. I mean, every type of redundancy, if you think about this as a function approximation, basically prevents you from having a sample somewhere else that might provide you with a better way of approximating that function. Right? I never encountered any case or any paper that said that other approach is actually better, but you might need to ask mathematicians about that. But my intuition is that no. That's a good question. Yeah, so this is the way it works. And what we're going to look at now is like how this can actually be used for, and yeah, the other thing is when you do, the other answer to this is in other contexts when you are not just using this for localization purposes, these particle filters are extremely powerful. Right now, like when we speak about localization, that is a relatively small state space for a vehicle like living on a plane, like that is x and y plus the orientation. And so it's a 3-dimensional state. I mean, throwing away 3-dimensional states is not very costly. But if you think about alternative applications with higher dimensional robots, like flying vehicles, 6-dimensional, or it could even be when you do this in other contexts, or when you add variables. For example, you can use particle filters also to estimate additional components of the state space. So we have, for example, used this for estimating the diameter of the tires of a wheel, of the vehicle. And the advantage of that is if you think about, for example, a forklifter that goes from A to B and lifts up the heavy loads, right? And when it picks up a load, then actually the diameter of the wheel shrinks, which means that you need to have a different motion model or transition model, right? Because I mean, when you sample from a model that takes into account the wheel diameter, then you can actually have better predictions and have the particles in better places. Which means that your state space is higher dimensional, and you invest a lot of time computing these higher dimensions, and then throwing away particles just based on a resampling operation might then be not very, very effective. And it can be really expensive. People have also used this for SLAM, so simultaneous localization and mapping. And then in the particle filter context, the entire map becomes part of the state of a particle, which then means that when you perform this resampling operation in the wrong fashion, you throw away an entire map, and that can be a huge fraction of your memory. So you invest a lot of calculations into these individual states that you then throw away using a suboptimal resampling operation. So typically you need to be very careful about that. Yeah, so again, like in localization, and just to give you like a few examples that actually works in practice and can be used for on real robots. Like that is how this is done. The proposal distribution is just the motion model, and the observation model is used to calculate the importance weights. So motion models, typically, like this is when you look at papers, they often refer to these banana-shaped distributions, right? And the best spot here is like this part, or here you also have kind of like a little banana over here, right? That's kind of dessert banana, right? That there you have there. And so this is a 2D representation of a 3D state. So this is a robot actually performs translational arrows in X and Y and a rotational arrow. And it's just a projection of these particles onto the 2D space. And this is actually calculated from this function P of X prime given X and U. And with 10,000 particles starting at 0, 0, 0. And then we pass like all of them through that motion model once. And in the very first case, that gives a distribution like this one over here. And if we again pass those again through that transition model, we get a distribution like this over here. And in the third step, a distribution like this over here. The interesting aspect is like this distribution like indicates something about the angular versus translational error. Right? So when it looks like a vertical, like a banana, that is kind of like a banana is that because in practice it's a little bit curved here. And so that is basically the case because we have a relatively high error in rotation here. So that model, this is a robot that does relatively high rotational errors. If you have low rotational errors in your transition model, then those particles will be peaked and this distribution will be more longitudinal because, I mean, it's more, let's say more circular because X and Y might be the very same. Depending, if you have more in X, which would be that direction, then it would be more longitudinal. If you have rotational errors, and that forces it to elongate along the Y-axis in this plot.
In this case, because every particle is equally likely when you resample, you have to discretize the state, right?
Actually, that is just like, this is the advantage of the particle filter over other representations, like histograms, is it just stores X, Y, and theta. It's just real numbers that you have. Every particle is a triple of real numbers, X, Y, and the orientation. And then you use this rejection sampling scheme through that function P of X prime given X and U. You pass it through, or basically we tend to say we calculate a potentially new space according to that transition model. That needs to be carefully designed. This is basically like the repeated operation of P of X prime given X and U. And here we sample that set from this set. Right? And basically what we're asking is, where would this particle end up given the operation by the robot? And this is basically that black line over here. I do not know what the units were. It's just for, it says 10 meters here, maybe something like 2 meters or something like that. Well, it's actually according to to a motion model where you can say, for example, a very, very simplistic one could be in every step we do have a normally distributed Gaussian error in the translation, right, in X, a normally distributed error in Y, and a normally distributed error in the rotation of the vehicle. Right? So basically use a normal distribution. You assume these errors to be independent, so you take your current hypothesis X and Y and theta, and you draw on X prime, Y prime, and theta prime according to this Gaussian, yeah? Which is centered at 2 meters, and then for X, and centered at 0 for Y, with different standard deviations, and centered at 0 for the angle as well, or the angle offset, and then you add those to your current hypothesis or particle, and this is where these positions end up. It's basically that operation. Did that answer your question? So that might be a motion model, and this is one of the observation models that you might use. So this is just the statistics, how often you actually measure a certain distance, given you have your map tells you how far things are away, given that state of the particle. Right? So given you have a map, right? If I do have a ultrasound sensor, and that tells me it's going to be 3.5 meters up to that wall over there, right? And my sensor points into that direction, giving the state that I'm currently in. Right? If another state looks like that, right, then the distance is larger, so it will have a lower likelihood. Right? Right? And in fact, like those states where I'm exactly 3.5 meters away from that, they're actually extremely likely, or more likely than others. And here is that plot for, I think this is, it doesn't matter, this is 2.30 meters or so, right? So it's basically according to the state of the particle in the direction of the measurement, that would be, I would expect in the map to measure 2 meters and 30 centimeters, something like that over here. And then we can read from this function, this red function is a typical likelihood model. We look at if the sensor measures like 2 meters, then that would be the importance weight. This can be done, implemented very, very effectively in just lookup tables. You basically can discretize your observation likelihood in case of low dimensional ones, and then just convert it into a lookup table. So every operation here for that likelihood importance weight calculation is just a lookup in a table. It's super fast, yeah, you need to pre-calculate this for all distances. It takes a little bit of space, but it can be done very, very effectively if you have dense depth measurements, for example. So this is a way how to get these importance weights. All right. So again, like this is with the operation that we want. What we want to interested in now, so resampling. We spoke about this, and this is an example of an application of this. This is a real data set. It's actually more than 20 years old, this data set, and these figures that you see here. It is one of the very first applications of this, used in that case data from Minerva, a robot that we installed in the Smithsonian Museum of American History in Washington, D.C. as a tour guide. And this is, and you can see in some cases like spurious measurements simply because people walk through that museum as well. And the goal of that robot is actually to perform global localization. So it uses its laser range scanner to measure distances. You see in gray the map that we used. So basically it just displays the borders there. Just for visualization purposes. The transitions between white and gray is actually where the obstacles, or the surface of the obstacles are. So what we have now in the very beginning is a randomly distributed set of particles. Random in X, Y, and orientation. Orientation is something we don't show here. So the first step, like this is the first measurement, depicted at the most likely state. It turns out that, this are actually us over here. We had our desks at that spot. So that corner is actually this one over here. So it's relatively close to the true pose. The problem typically is that you never have a hypothesis at the exact right spot in the very beginning. So it's kind of like a trade-off between how many particles you need or you want for initialization purposes, and also like what your computation time is that you can spend on a vehicle. Turns out that you will see that over time these particle sets actually converge to the true pose of the vehicle, and all these particles are located at the true spot of the vehicle, which means that for approximation purposes, you do not need to have 10,000 particles that as long as you are kind of like confident, or the system is confident where the robot is. And this is why there are also schemes of dynamically adjusting the number of hypotheses or particles, and so on and so forth. But let's first of all look at how that works. So we get, the robot is always depicted at the particle that is most happy, and the most happy particle is that one with the highest importance weight. And already here we see orientation is kind of okayish, and it's close to where it is. So what we do is we weigh these hypotheses, and darker means higher weight, right? And then we resample. We'll see this in a second, and you will actually see a better contrast there. All right, but here you can see a couple of hypotheses like emerging. So next step is that we calculate the importance weight again, resample, and then propagate according to the movement. You see now we are actually closer to the true pose. And the interesting aspect now is by the fact that through that resampling operation, we get more and diverse particles in the areas of high likelihood. There's a higher chance of actually getting closer to the true pose of the vehicle. So we accumulate more particles in the relevant areas of the belief there. Which means we actually, kind of like if you think about this, we are in a gradient and getting closer to the true pose. And this is a disadvantage of the particle filter. You never get the maximum of that. The maximum likelihood is like you can only get an approximation of that. And for that, you would need to have like optimization-based approaches, like smoothing techniques or something like that. So next, again, is like weighted according to resampling operation, propagating the particles. And now you see like how dense that gets. So all the 10,000 particles are close to where the robot actually is. And it actually nicely fits. Map is not accurate, as you see. Here you can see carefully that in the center, it's actually like darker, right? And if you keep going, it keeps accumulating the particles. And then whenever you do this prediction operation, the particles spread out because of the uncertainty in the robot motions. It's kind of like a trade-off between the prediction, where you actually try to capture everything that might happen from step t to t+1. Then you have the correction, the perception that tells you what actually happened. And that focuses the space again. And when you implement this, you need to carefully design those two components. This is why they are so super important. And here's another example of one of the famous videos of a robot performing global localization in a highly symmetric corridor environment with ultrasound sensors. And you see all these hypotheses, multiple hypotheses, simply because the robot doesn't know exactly in front of which door it is, which it can detect only by these measurements going through the doorways. And the corridor is also rotationally symmetric. This is why we have two peaks, and those can only be distinguished by entering one of those two rooms. Interestingly, because of the higher uncertainty there, at the end, the particle set also bifurcates. This is happening now. Do you see that? Because it might be the case that the robot actually had turned right, although the measurements are turning left. And then, if you keep going, that actually typically sorts out. But that doesn't mean that it always converges. Even a particle filter can diverge in cases where your motion model is not correct. Where you're overly optimistic with the motion model. That is a typical source of divergence, right? And the other one is if your observation model is not correct, or maybe also too strict. If it's too peaked, then you throw away too many particles in the resampling operation, right? So you might be overly confident about where you are. And here's another example also from Minerva. This was a robot, very same environment, and it's actually a super simplistic sensor model that is a ceiling mosaic at that time generated by Frank Dillard. of the, like, we had an upward-facing camera over here. And from that, we took all the pictures. And Frank was interested in mosaicing, so he generated the ceiling mosaic of the Smithsonian. And you see all the lights in there. And then I designed a super simplistic model for that. We basically took the center part of that image, of the current image, right, blurred because the robot is in motion and the floor wasn't even. So I took those, I think it was 10 by 10 pixels over here, and calculated the average intensity of that image. And then I had a very, very simplistic error function, which is basically nothing else but a Gaussian. I looked at the, looked up, like, given the state of the particle, like, what would the intensity in the mosaic? What is the intensity that, the average intensity that I measure? And then I used the Gaussian to basically do, like, it's basically the squared distance of those individual pixels. And then that gives you the likelihood. And once you do this, and I hope this video runs, so there are a couple of measurements that's actually interesting. If this is your center image, then maybe it's more, 20 by 20 pixels or so. And then you can actually calculate P of Z given X, given that mosaic. So for example, like, this is when you're under a light, and actually there where lights are, it's dark, means high probability. And when it's dark, it's a low probability. And then you do have, like, next to a light, then you can actually see in that distribution that there are black circles around the lights. So everywhere where you are around, like, close to a light, it's higher likelihood than anywhere else. And this is if you are under, when there's no light, then like, lights have very, very low likelihood. And if you let this run, this is a true trajectory. I think, again, 10,000 particles. So there's a yellow dot in here that that's here. This thing is, it's hard to see, but you can see from time to time, screen grabbing was not that good at that time. So you can actually, just with this super simplistic model, you can perform global localization as a robot just based on ceiling lights. And this is something that differentiates the particle filter from other types of filters like Kalman filter, that it is inherently able for doing this. A Kalman filter can also do global localization. It doesn't mean that it cannot do, but because of the low amount of linearity, it's actually more complicated. So what we basically can do, or what we have shown, is we can do global localization, which is pretty interesting. So you can like, initialize it, and it can keep track. There are extensions for that, for doing, like, dealing with localization errors. Kidnapped robot problem, that's popular in robot soccer, where you take the robot, put it to another place, and the robot has to figure out that it made an error, right, or that it's somewhere else now. There's several ways of doing this. People have started modifying that particle filter algorithm, but that's actually the wrong way. Right? The right way for doing this is changing your transition model. And there is the one way would be to basically guessing at every point in time that you are teleported somewhere else. Meaning that you need to have, in your motion model, need to have a component that says, I'm not taking your odometry, I'm guessing a random spot from time to time. And then you would actually, at every time step, you would guess that robot is somewhere else. 1 minute? Yeah, we'll be done in a minute. And there's one approach for doing this. Disadvantage is that the robot actually at every point in time guesses, oh, I might be in the Starbucks next door or so. And if all of a sudden the measurements are consistent with that, for whatsoever reasons, because there are people around, and it looks like the Starbucks restaurant, and all of a sudden all the probability mass will shift over, and the robot will actually believe it has been transited. And there's no reason for doing this when the robot is actually happy with its observations. So what people have been doing is either what I mentioned, randomly guessing new places, or the alternative is to look at the average likelihood of your observations. And basically, if they drop, meaning that the robot is unhappy with its observations, nothing fits really. So, and that is something that you can do. You generate the statistics about, like, what is the typical observation likelihood that I have when I'm happy. Then when you get below that threshold, you could even learn that. You could basically say, okay, I'm proportional to that, I'm guessing random locations. And the more unhappy I get, the more willing I am to accept being somewhere else. Right? And that's actually the most robust approach for doing that. That is the summary, and with that, I'm basically done. I hope you enjoyed it. I did it, and yeah, see you.
Sorry, start.
Thank you, Professor. I'll send you the email later. Yeah. Appreciate that.